In the previous lecture, we discussed the p-n junction diode. In the p-n junction diode, we talked about the depletion region. We calculated the depletion region width. We talked about the expressions for the electric field inside the depletion region inside the p-n junction diode. And then we also talked about the potential across the depletion width. And later we calculated the capacitance for a p-n junction diode. Since in a p-n junction diode we have separation of positive and negative charges, which results in a capacitance called the diffusion capacitance or the junction capacitance for a p-n junction diode. Now, that information of the p-n junction diode would help us understand the n-type MOSFET and p-type MOSFET. So, today's lecture is based on the metal oxide semiconductor structure. And if you understand the metal oxide semiconductor structure, you pretty much understand the operation of a MOSFET as well. So, let us go to slide number 17 so that we first talk about the operation of a MOSFET and later we focus on the MOS structure. In a MOSFET, as we previously discussed, we have a polysilicon gate. We can have metal as well, but as we discussed in the photolithography lectures that we mostly use polysilicon because of the reasons we discussed for fabrication processes of VLSI design. A polysilicon gate has higher melting point as compared to metal. So during the CMOS fabrication process, it's not going to melt down. So polysilicon gate is preferable as compared to metal in a MOSFET. So we have a heavily doped polysilicon gate. Then we have silicon dioxide. Then for an n-type MOSFET, the substrate would be p-type and the drain and the source would be n-type. Then in order to connect the drain and the source, we actually need a channel of electrons. Now the basic question is that the substrate is p-type, which means that the majority carriers in the substrate are actually holes. So where do the electrons come from the p-type substrate? Let us try to address this point initially and then we'll focus on the channel and the operation of a MOSFET. So actually there is a simple formula for the calculation of minority carrier electron concentration in a p-type substrate. The formula is N times P is equal to Ni square, where N represents the electron concentration, P represents the hole concentration, and Ni represents the intrinsic carrier concentration. As well, we know that the intrinsic carrier concentration for silicon at room temperature is 1.5 into 10 to the power of 10 per centimeter cube. Roughly, we can assume that intrinsic carrier concentration for silicon is 10 to the power of 10 per centimeter cube. So, Ni square would become 10 to the power of 20. Generally, for the substrate, the carrier concentration is of the order of 10 to the power of 15 or 10 to the power of 16 per centimeter cube. So, assume the whole concentration for the p-type substrate is 10 to the power of 15 per centimeter cube. Then according to the formula, N times P is equal to Ni square, then the electron concentration is equal to 10 to the power of 20 divided by 10 to the power of 15. Or the minority carrier electron concentration in this substrate would be 10 to the power of 5 per centimeter cube. Similarly, if the whole concentration in this p-type substrate is 10 to the power of 16 per centimeter cube, then the minority carrier electron concentration would be 10 to the power of 20 divided by 10 to the power of 16 or 10 to the power of 4 per centimeter cube. This number 10 to the power of 4 or 10 to the power of 5 electron carrier concentration per centimeter cube seems really low, but we also know that in current technologies this length between the drain and the source is really narrow, a few nanometers. So for this small channel we don't really need a high concentration of carriers. Even if we attract a small number of carriers towards this surface, it's going to form the channel between the drain and the source, connecting the drain and the source for smooth operation of a MOSFET. So we need to find a way to attract those electrons towards the surface. So if we apply a positive potential to the gate, it would attract those minority carrier electrons towards the surface, resulting in connecting of the drain with the source. And similarly for a p-type MOSFET, we would need to attract holes towards the surface to form a channel between the drain and the source. Also, in this MOSFET, we call this region the bulk region, and this region close to the oxide, the surface region. So we need to attract carriers towards the surface region in order to form the channel, resulting in connection of the drain with the source. This is the basic operation of the MOSFET. We also discussed in the previous lecture that we have several type of capacitances in a MOSFET structure, and one of the performance metrics of VLSI design, which is performance, or we can call it a quality metric instead. One of the quality metrics of VLSI design is performance, or we can also call it delay, is based on the resistance times the capacitance, or it's based it depends on the RC time constant inside a MOSFET. So we have several sources of capacitances in a MOSFET. First, as we can see over here, we have a metal gate or polysilicon gate over here, and then we form a channel of electrons for an n-type MOSFET. So basically we have two conducting regions, and these two conducting regions sandwich a dielectric, an oxide, silicon dioxide over here. So it kind of acts as a parallel plate capacitor. So this is one kind of capacitance in a MOSFET. Similarly, in the previous lecture we also discussed the operation of p-n junction diode. Here we have an n-type region, and here the substrate is p-type. So at this edge we actually form a p-n junction, and we know that in a p-n junction there is a diffusion of carriers across the metallurgical junction, resulting in a depletion region, and the depletion region is actually void of electrons and holes. So inside the depletion region we have fixed positive and negative charges, and we know that separation of charges actually results in a capacitance, and this capacitance of the p-n junction is called the diffusion capacitance, or it's also called the junction capacitance. Similarly, we have junction capacitance over here between the source and the substrate as well. Also, we are going to learn in the next lecture, but we can see over here that the source is heavily doped, and some part of this source actually overlaps the gate. Similarly, some part of this drain actually overlaps the gate, and these overlaps result in another capacitance, and this capacitance is called the drain to gate overlap capacitance, or source to gate overlap capacitance. So let's focus on the metal oxide semiconductor structure as for today. And if we understand the metal oxide semiconductor structure, we pretty much understand the operation of a MOSFET. With that context in mind, let's start from slide number 3. Here is the MOSFET structure. In the MOSFET structure, we have polysilicon gate, we have a semiconductor substrate separated by oxide, where T oxide actually represents the thickness of this oxide. Here is the energy band diagram of a metal oxide semiconductor, where E naught actually represents the reference level or the vacuum level. EC is the conduction energy level. EI represents the intrinsic energy level, which for semiconductors at room temperature lies around the middle of the band gap of a semiconductor. So, for example, for silicon, the energy band gap is 1.1 electron volts. So this intrinsic energy level would be around 0.55 electron volts. And then we have a valence energy level. Now, in this energy band diagram, we are actually talking about a p-type silicon substrate for the metal oxide semiconductor structure. So in the energy band diagram, we can see that the Fermi energy level for this case is close to the valence band, signifying that this is a p-type semiconductor. If the Fermi energy level is close to the valence band, it means it's a p-type semiconductor. And if it is close to the conduction band, it means that would be an n-type semiconductor. So it's actually a p-type semiconductor. Phi Fp over here, we talked about it in the previous lecture, is the Fermi potential, or the difference between the intrinsic energy level and the Fermi energy level. And there is an equation for the calculation of phi Fp, which we discussed in the previous lecture. Similarly, there is another parameter, it's called chi, or the electron affinity of a semiconductor, which basically means moving an electron from the conduction band to the vacuum level. For silicon, the value of chi is 4.15 electron volts. For a p-type silicon substrate, the Fermi energy level is close to the valence band, and the Fermi potential, which is the difference between intrinsic and Fermi energy levels, is calculated using this expression which we derived in the previous lecture. Here kT by Q is the thermal potential, 0.0259 volts, roughly it's 26 millivolts. In I represents the intrinsic energy level, and in A represents the acceptor doping. Similarly, for an n-type silicon substrate, the Fermi energy level would be close to the conduction energy level, and its Fermi potential is represented with phi Fn. We can calculate it using this expression where Nd now represents the donor doping. For today's lecture, we will focus on the p-type silicon substrate. If the substrate is p-type, the drain and sources would be n-type, implying that we are actually referring to an n-type MOSFET. So in today's lecture, we'll focus on a p-type silicon substrate, a metal oxide semiconductor structure where the substrate is p-type. Let us look at the energy band diagram of the MOS components of the metal, oxide, and semiconductor components separately when they are not placed together, or we can say let us look at the energy band diagram of each one of them independently when they are not connected. For the metal, assume that the metal is aluminum. We know that for metals, the conduction and valence energy levels actually overlap, and the Fermi energy levels is roughly around the same level as that of the conduction and valence energy level. We have a parameter, it's called the metal work function. It's actually the energy difference between the vacuum level and the Fermi energy level. And it means to move an electron from the Fermi energy level to the vacuum level. For aluminum, its value is 4.1, but for other metals, it's going to have a different value. For the oxide, we know that oxide is an insulator, so it's gonna have a really wide energy band gap between the conduction energy level and valence energy level. For silicon dioxide, its value is 8 electron volts. And chi for silicon dioxide, or the electron affinity for silicon dioxide, is 0.95 electron volts. For the silicon semiconductor, the energy band gap is 1.1 electron volts. Phi Fp, or the Fermi potential, is the difference between intrinsic and Fermi energy level. Similarly, chi is the energy difference between vacuum level and the conduction energy level. For silicon, the value of chi is 4.15 electron volts. The work function for a semiconductor is the energy difference between the vacuum level and the Fermi potential. So it's basically E vacuum minus EFP. Or it's actually the addition of several energy values. The work function for this semiconductor, which is p-type, is the addition of the electron affinity chi, which for silicon is 4.15 electron volts, plus EC minus this Fermi potential. As we discussed in a p-n junction diode, that a p-n junction diode has a certain built-in potential, resulting in a barrier for the flow of carriers to move from one side of the junction to the other side of the junction. So similarly, for a metal oxide semiconductor, we will have a built-in potential given by phi m minus phi s, where phi m is the metal work function, difference between the vacuum level and Fermi level for the metal, and phi s represents the semiconductor work function, the difference between the vacuum level and this Fermi energy level for the p-type semiconductor. We can calculate it using this simple formula. The work function of the semiconductor is equal to Q chi, where chi is the electron affinity, plus EC minus EF, this energy difference between the conduction energy level and the Fermi energy level. Why do we have the Q sign over here? We have the Q sign over here because the metal work function, the semiconductor work function, and the electron affinity are actually potentials or voltages, while everything else are energy levels: the vacuum energy level, the Fermi energy level, the conduction energy level, the valence energy level. So everything else are energy levels. So in order to represent these potentials in terms of energies, we multiply Q with it, because energy is equal to charge on electrons times potential. So that's why we add the Q sign with all these potentials. Now in slide number 9 we are talking about all these the metal, oxide and semiconductor independently. But what happens if we place them together when we form a metal oxide semiconductor structure? So similar to a p-n junction diode, under thermal equilibrium or under zero applied bias, we know that we should have a constant energy level first. And for that constant energy level, we need to bring this Fermi energy level upwards. And when we bring this Fermi energy level upwards, the valence energy level, the intrinsic energy levels, and the conduction energy levels would be bent upwards, which we can see in the next slides. Here is a representation of the energy band diagram of a metal oxide semiconductor structure under thermal equilibrium, where we see that now we have a constant energy levels, and the valence energy level, the intrinsic energy level, and the conduction energy levels are now bent upwards for reasons that we discussed in the previous slide. And here we have a built-in potential for holes. Since this is a p-type semiconductor, so we have this built-in potential, as you can see over here. there is a potential for holes to move from the semiconductor side to the oxide and to the metal side. So this built-in potential can be calculated using the formula given in slide number 9 over here. Let us consider an example. In this example, we consider a metal oxide semiconductor structure where the substrate is p-type. Then we consider silicon dioxide layer and a metal which is aluminum. We know that the work function of aluminum is 4.1 electron volts. The Fermi potential value is given, phi Fp is equal to 0.2 electron volts. So this value is given. The difference between the intrinsic energy level and the Fermi energy level is called phi Fp, and its value given in the example is 0.2 electron volts. So we are asked to calculate the built-in potential difference across the metal oxide semiconductor system. And we know that the built-in potential can be calculated using this simple formula, phi m minus the work function of the semiconductor, which is actually the addition of chi plus EC minus EI plus EI minus FP, or otherwise we can say it's the addition of chi plus EC minus EF. Now, in that example, this value is given. Phi Fp is given. It is 0.2 electron volts. EI minus EF is 0.2 electron volts. And we know the value of chi as well. So, if we calculate EC minus EI and add these three together, we actually get the work function of the semiconductor. We know that intrinsic energy level pretty much lies in the middle of the band gap. So if the band gap is 1.1 electron volts, then EC minus EI would be 0.55 electron volts. So then EC minus EF becomes 0.5 plus 0.2, 0.55 plus 0.2, 0.75, and then add 4.15 with it. It gives you the semiconductor work function. So the semiconductor work function is equal to 4.15 chi plus 0.75, which is the addition of 0.55 plus 0.2 is equal to 4.9 electron volts. And then the built-in potential is equal to phi m minus phi s, the work function difference between the metal and the semiconductor. The metal is aluminum, for which the work function is 4.1 electron volts, and the semiconductor is silicon, for which the work function comes out to be 4.9 electron volts. So 4.1 minus 4.9 is equal to minus 0.8 electron volts. So this built-in potential over here is actually minus 0.8 electron volts. Now, as we can see that under thermal equilibrium there is band bending. Is there any way to flatten these energy levels, to flatten the valence energy level, the intrinsic energy level, and the conduction energy level, when the built-in potential is minus 0.8 electron volts, or minus 0.8 volts, right? Electron volts. So, if this built-in potential difference is minus 0.8 electron volts, and if we apply plus 0.8 electron volts to this metal oxide semiconductor structure, all these energy levels, the conduction, intrinsic, and valence energy levels would flatten. So the plus 0.8 volts is actually called the flat band voltage, because it's going to flatten the energy levels. So VFB is equal to phi m minus phi s, or plus 0.8 volts would actually flatten all these energy levels. That's why it's called the flat band voltage. There are different modes of operation of metal oxide semiconductor. There is accumulation mode, then the depletion mode, and we also have an inversion mode. The MOSFET is operated mostly in inversion mode of operation. Let us discuss each one of them in detail. In the accumulation mode of operation, we actually apply a small negative voltage to the metal part. or to the polysilicon gate part. And this small negative voltage would attract holes from the p-type silicon substrate. So now holes are going to be accumulated at the surface. This region is the bulk region, and this region close to the oxide is considered as the surface region. We can also see the effect of this small negative voltage on the energy band diagram. We discussed in the previous lecture that when we apply a small negative voltage to this part, it means relatively we are applying a small positive voltage to the semiconductor side. And according to the simple equation, E is equal to minus charge on electrons times voltage, the side to which we apply positive potential, its energy levels would be dragged down. So as you can see that now the Fermi energy level on the semiconductor side is dragged down as compared to the Fermi energy level on the metal side. And the gate voltage is accommodated across these two Fermi energy levels. So as we saw that holes are actually attracted towards the surface in the metal oxide semiconductor structure, we can also see that effect in the energy band diagram as well. In the energy band diagram, we see that in the bulk region, away from the surface region, the Fermi energy level is close to the valence band, which means here we have a p-type semiconductor. But as we get closer towards the surface, we see that now the Fermi energy level is now getting closer and closer to the valence band. And right at the edge, at the surface, now we see that it now coincides with the valence energy level, which means we have high concentration of holes at the surface. So this effect is obvious both from the metal oxide semiconductor structure and from the energy band diagram as well. The second mode of operation of a metal oxide semiconductor structure is the depletion mode of operation, in which we apply a small positive potential to the gate. When we apply a small positive potential, it will repel holes from the surface towards the bulk. When it repels holes, it leaves behind fixed negative charges in a p-type region. So this region over here would be depleted of holes, leaving behind fixed negative charges. We can also see that effect in the energy band diagram. We are applying a positive potential to the metal side, which means that the Fermi energy level on the metal side would now be dragged down as compared to the Fermi energy level on the semiconductor side. So now this Fermi energy level on the metal side is lower as compared to the Fermi energy level on the semiconductor side, because we are applying positive potential to the metal. And now we also see that there is downwards bending now in the semiconductor side. So because of that effect, now we can see that this metal oxide semiconductor structure actually does not have any carriers in this depletion region. Similarly, looking at the energy band diagram for the metal oxide semiconductor, we see that in the bulk region, the Fermi energy level is close to the valence band, right? Indicating this is a p-type semiconductor. But at the surface, we see that now the valence band is actually bending away from the Fermi energy level, indicating that here we have less number of holes as compared to the bulk region, right? And we can also see that effect that now the intrinsic energy level is actually coinciding with the Fermi energy level right here at the surface, right? Which indicates that at the surface it's acting just like an intrinsic material, where we don't have any carriers, we don't have electrons, and we don't have holes at the surface. So it's acting just like an intrinsic semiconductor. This is depleted of carriers. So that's why it's called the depletion mode of operation. And we can also see that effect in the metal oxide semiconductor field effect transistor, the MOSFET structure over here, where we see that if we apply a small positive potential to the gate, we have a depletion region depleted of carriers around the drain region, under the gate, and around the source region. In this depletion region, holes are actually repelled by the small positive potential. The next mode of operation, which is also crucial to us, is called the inversion mode of operation. In the inversion mode of operation, we apply a large positive potential to the gate. So if we apply a large positive potential to the gate, it actually attracts electrons towards the surface from the p-type substrate. As we discussed that electrons are minority carriers in the p-type substrate, but if we apply large positive potential, it's going to attract electrons towards the surface. Similarly, since this is a positive potential, it will repel holes as well from this surface, from this region which is close to the surface. So it's going to introduce a depletion of holes in this region and an accumulation of electrons, which is called inversion as well, because substrate is p-type, but at the surface we have excess of electrons. So that's why it's called the inversion mode of operation. We can see the same effect in the metal oxide semiconductor as well. We are applying a large positive potential to the metal oxide semiconductor. Applying positive potential here means that the Fermi energy level on the metal side would be dragged down as compared to the Fermi potential on the semiconductor side. So this Fermi level on the metal side is now lower as compared to the Fermi level on the semiconductor side, and this gate voltage is accommodated between the Fermi levels on the semiconductor side to the Fermi level on the metal side. Also, if we look at this energy band diagram, we see that away from the surface in the bulk region, the Fermi potential is close to the valence band, which means this is a p-type semiconductor. But at the surface, now we see that this Fermi energy level is above the intrinsic energy level, and it's close to the conduction band instead of the valence band. So if this Fermi energy level is close to the conduction band, it means that here at the surface we have more number of electrons now. We have majority of electrons. We have the inversion layer, which actually forms the channel. This is actually a channel of electrons here at the surface. So it's called inversion mode because the Fermi energy level is now closer to the conduction band as compared to the valence band. So at the surface we have majority of electrons, but in the bulk region still the Fermi energy level is close to the valence band. So in the bulk region we have majority of holes. And we actually operate MOSFET in the inversion mode because consider an n-type MOSFET where the drain and the source are n-type. So in order to connect the drain and the source regions, we actually need a channel of electrons. So we apply a large positive potential so that it can result in the attraction of electrons from the bulk towards the surface, forming the channel, and at the same time it will repel holes from this surface region, resulting in a depletion of holes as well around the drain and the source region and underneath the gate as well. The surface potential. The surface potential, represented with phi s, is the difference between the intrinsic Fermi level at the bulk minus the intrinsic Fermi level at the surface. So it's actually equal to EFI bulk minus EFI surface. As we discussed that in the MOS structure, at the inversion mode of operation, we have a depletion width. Whenever there is band bending, it actually represents the depletion region. So inside this region, where we have band bendings of the conduction band, of the intrinsic Fermi energy level, and of the valence energy level, we have a depletion region. We have fixed negative charges for a p-type substrate, and this depletion width is represented with xd. For the metal oxide semiconductor structure, the entire depletion region is almost accommodated inside the semiconductor. And we got a simple formula for calculation of this depletion width. It's equal to 2 times permittivity of the semiconductor times the surface potential, which is represented over here, the difference between EFI bulk minus EFI surface, divided by charge on electron times the acceptor doping. Or here is another way of representing, since I told you that the entire depletion width is accommodated inside the semiconductor. So WD is equal to, here is another representation of the same formula. Now, as we discussed that there are fixed negative charges inside this depletion region, for a p-type semiconductor, holes are repelled from this region, leaving behind fixed negative charges. These charges have a certain depletion region charge density in coulomb per centimeter square, and it can be calculated using this simple formula. Q is the charge on electrons, and A is the acceptor doping, and WD is the depletion width. So replace this value in this formula, and we got a relationship for the calculation of the depletion region charge density in coulomb per centimeter square. Here in A is the acceptor doping. Epsilon represents the permittivity of the semiconductor. For silicon, its value is 11.7 times 8.854 into 10 to the power minus 14 farad per centimeter. Now we are actually leading towards the calculation of the threshold voltage, the voltage which results in the inversion layer, the channel of electrons which connects the drain and the source. So I'm going to save the recording so far, and then in part 2 of this lecture, we will reconvene after around 10 minutes.